So let's get started. So as you probably know, the homework is due on Wednesday. So the turn-in will be through Canvas. So actually, I've never done this before, this Canvas. I'm hoping this works. I've been assured by some people it's very easy, but hopefully Razor or someone will post how to do it on Canvas if you haven't done it before. Or if you're not done before either, no. So it looks like it should be easy, but if there are, hopefully, if we have trouble with the turn-in, we'll figure something out how to deal with it. But hopefully you'll be able to turn in a PDF document in through the Canvas system. So has anyone done this before? Okay. And so it's pretty easy to do? Yeah, it is. Yeah, okay. Okay, good. So crowdsourcing. So the other thing that's coming up is the first part of the project is already due next week. So the first thing is the project proposal. So this will not be turned into Canvas. You'll give me a hard copy of this. So give me a one-page printout. So I've talked with some people already about what this is supposed to be. Is there a question? So just to review, what is the scope of the project? So I'm hoping that this is supposed to be a more applied component of the class. The data sets and homeworks we'll use will be kind of cleaned a little bit, so you won't have to mess around with them. But when you're dealing with real data, you actually have to work with starting in whatever format your data is. You need to make decisions about modeling, and you have to decide on your own which techniques to apply, as opposed to doing exactly what it says to in the homework. So that's what I'm hoping. If you can kind of demonstrate those three things in the project, then that's probably good. So more specifically, what are options for good projects? One is finding some data set, getting into a format and applying, some technique from class, and then trying to, have a small discussion about how you thought it worked, right? So if you're doing, I think unless you talked to me about this, I assume you're doing a project in a group with 2 or 3 people. So one good thing would be there are different variants of some of the techniques we'll cover in class. We'll talk about various different clustering algorithms, various algorithms for doing similarity search. And one way would be to take a data set and compare these 2 algorithms, say which one works better than the other one. So if you're doing with several people in the class, you can each try and work with one algorithm. And what I'm hoping is, if it's a combined project, a group project, it should be clear the aspect of each person in the group. So I'm able to see that this was more than just a one-person project. You should be able to cover a bit more that way the larger the group is. And one other thing that some people have done is they've taken something from class and they've proposed some extension of it. This doesn't need to be on the level of a research paper, but it should be kind of, some variant of it, and sometimes this works better. Sometimes you need some extension to apply it to a particular data set because the modeling doesn't quite work. So if you have questions still, these are good things to work on. My office hours are Thursday afternoon. That's a good time to come by and chat with me about that. Or you can send me a short email with the basic idea. Just remember the project proposal, so it's 5 out of 100 points of the project, so this is 2.5% of your total grade, so don't forget it. It should have who's in your group, what data you're planning to use. You don't need to get the data yet, but you need to kind of have an idea. And if you don't have a good source, I may be able to point you to a better source. What structure are you planning to mine from the data, or what technique are you planning to use from class? You don't need to say the details yet, but kind of get a general idea of what you're planning to do. And also, just to make sure that this is not some boring application of stuff, I'm hoping you can tell me why the problem is interesting, right? right? Maybe why it's interesting to you, why I would find it interesting. You know, part 5 is, you know, you don't necessarily need to have these 5 bullets, but, you know, what would I learn? What would I learn from reading your project? If you're comparing 2 different techniques, maybe I'd learn this one works better than the other for this sort of data, right? So it's more enjoyable for me, you know, this is, you know, for my own sake, I'm hoping to get a little something out of this. And hopefully if you aim for one of these, you'll also get out of it, and you'll have to do a presentation at the end with a poster, and your other classmates will hopefully learn from this as well. So any questions on the project proposal? General questions? Any specific questions, you can email me or find me briefly after class or in office hours. All right.
I have one question.
Yep.
What's expected of us in the second part of the question 4?
Second part of question 4.
Yeah, so in the homework one. Or
yeah, so there was some discussion on, there's some part on the discussion group. Have you read that?
Yeah.
Yeah, so the question 4 in the homework, I think I accidentally made this a little harder than I anticipated. So the answer I originally had imagined, I think is probably not feasible. So I'm hoping for you to at least discuss the challenges of extending, of getting, if it's possible to get more random numbers with roughly with fewer than just multiplying that many more random bits. If you can do better. I believe there is a way to squeeze a little bit more out of it, but some discussion on that, you know, to show you understanding the issues there will be in. So it's, I think I probably would have answered the question, asked it differently if I'd done it over again, but I'll leave it up there for now, and I probably won't be too harsh on that, but if you can come up with a technique to reduce the number of random bit calls, then that would be great. You may end up getting some bonus points. Okay. All right, so let me turn this off. So today we're going to talk about computing the Jacquard distance, and in particular using a technique called min-hashing. And I think this was by Roeder et al., and I think in 97 or so. So there's a couple of papers and a couple different co-authors, but I think it's generally attributed to Andre Roeder. So just review the Jacquard distance or Jacquard similarity. So we'll use as a consistent example, I'll write it here in the middle. We'll look at a few sets here. So we'll use this as the consistent example. And so the Jacquard distance between, or the Jacquard similarity between 2 sets, let's use example S1 and S3 is going to be the intersection between the size of the intersection between the 2 sets over the size of the union between these two sets. Okay, so the intersection, here they only have one value, 2 in the intersection. And there are one value 2, so the value 1 here. And the total size, the union of the two sets is going to be 6. All 6 elements are in the union. So the Jacquard similarity is going to be 1/6. The higher this value is, the closer to 1, the more similar these sets are. Okay? And so we talked about on Wednesday how you can use these techniques like these K-grams to convert text documents into sets, and then this gives a nice similarity between these documents doing this conversion. But one of the issues with this is that, you know, if you're trying to compute this, you have to compute the intersection between these sets. The union is not so hard, the size of this intersection. The union is not so hard if you know the size of the intersection, because you can keep the counts of the two sets. So I ask you to think about how would you go about computing this. Did anyone think about that and come up with the answer? Yeah.
If you knew the range of possible values of elements in each set, and let's say we set an array, and then just traverse over the first set, and just kind of put something in each bin number for each thing in the first set, and then just traverse over the second set, and then, you know, for each bin that already has something in it, then you know that element is in the intersection.
Yes.
That would be about the smallest I can think of.
So you can actually do something with a little bit without using extra space. So you say run over it and keep track of something, then go over the second set.
You could hash them. So it's like maintain a hash table now where your lookups are constant. You basically just you're really going over the entire thing once there.
So the idea is to take both of the sets and hash them both to a hash table, so you have the secondary storage, and then count how many collisions there are in the hash table. And that gives you an estimate. So those are both okay. They both take about, they both take linear time, and they both need linear in the size of the sets. And they both, so you have to look at every element in the set. And they both, need a linear amount of extra space as well, at least. You're writing it down in a different format every time. So if you're maintaining these sets, one thing you can think of is, I'm going to maintain them in a way that they're easy to compare. And one way to do that would be, like they are here, keep them in some sort of sorted order. Most elements, you can define sort of ordering over them, so there's a consistent sorted order. And then you can use a similar technique and scan both of the lists at the same time, always going to the one that's next in the total sorted order, and then you can always see if there's a collision. You can do this without writing anything down extra. So you can just do a parallel scan over both of these. It's a little trickier than implementing a single for loop, but you can do it in a single loop. But you can do this in linear time if you have them in a sorted order. But this is still a little bit clunky to do. You could have that so this was kind of invented for comparing web pages to see if two web pages are very similar to each other. And web pages have a lot of text, can have a lot of text on them. And every time you compare them, you don't want to scan over the entire web page, which essentially is what you would need to do to use this technique, or scan over some stored representation of the web page. You don't necessarily want to do that. We're going to come up with a way of comparing them, which will essentially be constant time in the size of it's not going to depend on the size of the sets. Now, you're going to need to do some pre-processing for each of the sets ahead of time, right? But to create the sets, you need to do pre-processing. You needed to do this, you're creating these K-grams when you're doing this. So in the same step you're doing these K-grams, you're also going to create a representation of these sets, which is going to be easier to compare. And by saying constant time, that's lying a little bit. It'll depend on some error parameters. There's going to be an approximate technique, but we'll get to that. But it's going to be independent of the size of how big these sets are. So, but it seems like that should be very hard to do to get a good, accurate estimation. But we'll kind of walk through this a little bit. Okay, so the main idea we're going to be, so again, we're going to build on these ideas we talked about Wednesday of converting into a different abstract data type. And this other abstract data type will be easier to tell the distance between two things. And so the first thing we're going to do is, well, so we had this first step that went from the document to a set. And then we're going to go to the set to a matrix. And so this matrix will be easy for us to understand what's going on, but it's going to be a really clunky representation we're not going to want to use. So we're actually going to not really go to this matrix, we're actually going to go to a vector, and I'll show a second how to do this. So we'll skip this step here, but I'll first show you this representation, how to think about the problem, and then show how to go straight to a vector, and then we can compare two vectors, short vectors, very quickly. We'll talk about this. Okay, so how would we represent these sets? So I'm gonna have a group of these sets and represent all of them, all of the sets as a single matrix. Does this make sense? So how would we do this? So if you have a matrix, you're going to think of having this as a table. So you're going to have sets S1, S2, S3, and S4. And then for each row, you're going to correspond to one of the elements. Okay, and then all the matrix will store is there's a 1 in the matrix if the element is in the set, and a 0 otherwise, right? So for set 1, it has 1, 2, and 5, and the rest of these are zeros. For set 2, it only has element 3. The rest of these are zeros. Set 3, it has 2, 3, 4, and 6. And set 4 has 1, 4, and 6. Okay? So this representation captures the exact same information as the sets here, right? So I can go back and forth between these. I haven't lost anything here, but this is kind of a stupid way of representing it. I've added a bunch of these zeros in here essentially, and typically in the examples we had, the number of potential elements could be very large. And one of the nice things about the Jacquard distance is it didn't have the notion of how many possible k-grams could you have in order to define this distance here. Whereas some of the other things like the Hamming similarity needed to know the total number of possible k-grams. So in this representation, if I were to really write this out, I'd have to go and write out all of these different rows for all these different elements. But that's okay, so I'm not done here yet. And so in fact, when you have this case where the number of rows is going to be much, much larger than the number of ones, that's typically called a matrix that's sparse. So this is for a matrix with most entries as 0. So usually the 1 or something else, some other numeral is representing the information, and 0 is the lack of information. And so these will be very sparse matrices. Okay, so this is a very wasteful representation. So, but now I can I can calculate the Jacquard similarity between two of these columns here by going and seeing the intersection is now how many of the rows both have ones in them. That's going to count my intersection, right? So if I look between set 1 and set 3, I can go across and calculate the number of ones where they both have a 1, right? So this is the only row where both of these have a 1. That's any place else that set 3 has a 1, set 1 is 0 here. Okay, so this information is still captured. Okay, so I went away and I'm going to use some randomized techniques to calculate this faster now. I'm going to use this idea that the rows that have both ones, they both have ones in them are the interesting rows. Actually, there's other interesting rows as well that I need. The rows where one of the two sets has a 1 in it. If both sets have a 0, let's say I'm calculating between set 2 and set 4, this row, they both have a 0. So this one does not play in the top or the bottom. In fact, most of the rows will be like that. So I somehow want to find all these rows with intersections and somehow throw away the rows that have both zeros. Okay? So I'm going to first describe a technique which is not really the right way of doing it. And we'll discuss this, and there may actually be some statistical reasons why some version of this might not be so bad. But this will hopefully start to give you the right idea of what's going on here. So this would be called hash clustering. Okay, so the idea is I'm going to create some sort of hash function which is going to go from my set of all elements to a set of clusters. Okay, so I'm going to kind of group some of these rows together. Each of the elements will be one of the rows here. So this, let's say that this set in our example is going to be A, B, and C. Okay, so we could think of a couple things. This could be some sort of randomly chosen hash function, so that which cluster it falls in is going to be somewhat at random. And maybe this would be useful for analysis, or maybe these are clustered based on the categories that the sets are in, and maybe this gives extra support of whether something is in one of these sets. So if I did this, so let's say that this function was actually defined as from where these map to my example matchup. All right, so this hash function is going to be deterministic once it's picked. So every element 1 will map to a value A, and this set will be smaller than the total set. Okay? So then, if I look at the resulting table I got, instead of this kind of matrix or table here, I'm going to get a smaller table. Right? And I can have, say, if I only ever had 3 clusters, which is probably way too small, but if I only ever had 3, then no matter how many rows I had, I only have 3 rows to check here. And so now the answer looks like this. Right, so if anything in this set has, if any one of these things has an A in it, okay, so let's look at set 1 here. 1 hashes to an A. So I have an A. 2 hashes to a B. So I have this B here. A B, and the other element here is a 5. 5 also hashes to A. So I already have that. So I didn't need to keep track of something else. now if I want to look at the Jaccard similarity defined on this matrix here, well, it's going to be faster now. I don't have as many rows to check, right? So let me write up the Jaccard similarity before and after, just to show here. So this is Jaccard similarity, and this is the Jaccard similarity with clustering. And so this was 1, 2. Right, so for 1, 2, the right answer here should be 0. Let's see, I messed up my example somehow. This should be 1/6. 1 and 4. This is going to be 1/5. 2/3, 2 and 3. This is going to be 1 out of 4. 2 and 4, 0, and 3 and 4 is going to be 2/5. Right? So what do you think is going to happen to these numbers when I do this clustering? Am I getting? So you think they'll always go up? Okay, so let's see what happens. So they'll either go up or they'll stay the same. All right. So let's see how this works with my example here. So 1 and 2, they're going to be. This used to be 0. Now the value is going to be 1/3. Oh no, 1/2. 1 and 3, it's going to be now 2/3 instead. So 1 and 4, now I have 1/3. 2 and 3, I'm going to have 1/3. 2 and 4, going to have 0 again. And 3 and 4, I'm going to have 2/3. All right, so it looks like in this example, all the numbers have either gone up or they stayed the same. Right, so it seems like it's probably not unbiased. What's happening here is sometimes there was not a collision, and then you because two different things clustered to the same thing, to the same cluster, then it looks like there's a collision, even though they didn't have any elements the same, right? So that was at least the case here for the between sets 1 and 2. But it's not always going to be the case that these numbers are going to go up. In fact, sometimes the numbers will actually go down. What can happen is that the number of intersections can stay the same, but the union might decrease, right? So that, let's see. So if this number, wait.
Union will increase, right?
Yeah. So let's see. So how does this work? So all right, so I think there's an example, I don't remember right now, where you can get it so it actually goes down, but
the intersection
maybe
might remain the same, and union might
Goes down,
go
goes
a
up.
little bit up.
well, the union can't increase, but relative it can. It could be that the union is almost the same, it goes down by a factor 2, but the number of intersections goes down to 1. Right? Everything that intersects maps to the same set, and only those things map to different sets. Everything else stays in a distinct set. Right? So you can have an example where So you could go from something like 2/4 to you need bigger numbers here. So you need something like we could go like 2/5 to 1/3. Good. Good. So you have like 1, 2. So set A would be 1, 2, 3, and B would be from this would be 2. How would this work? So this would be started at. We want to go from 2/5 to 1/3. So we need. Let's skip 4 here. Okay. So here we have the intersection. We want 2/5 to 1/3. So okay. So let's do this. So the intersection now is 2/5. 2 and 3 out of 5 total things, and now if they map to, if you had things where 1 maps to A, 2 and 3 both map to B, okay, and 4 maps to C, and 5 maps to D. Then what you're going to get is, afterwards, your intersection is going to be only at B, where you'll have 4 total things who go from 1/2 to 1/4. So maybe I screwed this. So if there's confusion, we'll come back to this after class. I'd like to kind of so. Try and do this on the fly. I think I may have messed this up. Is this right, or? I think it's. So I went from 2/5, and now I'm at 1/4. Right. So this is decreased. Right? No. Yeah. So 0.4 to 0.25. Okay. So this hash clustering, it's hard to say a lot about this. So you may be able to somehow use some ideas like this to kind of get a better support for each of your bits of information, but it's not really, you're somehow compressing the table in a way that's good, so you can do this more efficiently, you're less storage, but it's hard to say how accurate this is going to be in estimating the card distance, which is what you want to do. Okay, so this technique does not quite work. All right, so let me try and describe this min hashing now. Okay, so it's going to have 3 steps here. So step 1, I'm going to randomly permute on the ordering. Okay, so I'm going to randomly permute the ordering of the elements. So instead of ordering them 1 through 6, I'm going to change this up. So let me write an example here. And you don't actually, we'll see, you don't actually need to do this full random permutation, but so it's easier to think about this way. So we'll do 2, 5, 6, 1, 4, 3. Okay, so now I'm going to redraw this table. Okay, so now I want to look and see which elements are in which set. I'm going to recreate a matrix representation here. So I have 1, 2, and 5. Set 2 only has 3. Set 3 has 2, 4, and 6. 2, 4, 3, 6. Okay. And set 4 as 1, 4, and 6. So did I make any mistakes, or did I do this right? Okay. So the first step is do this randomly permutation of the ordering of the elements here. Okay, then step 2, I'll record the smallest element. In each set. Okay, so now I'm going to have a vector m, or a function m, which is going to go from the set number to whichever element has the smallest, which is actually in the set. So S1 is going to give me a value of 2. According to this new permutation, this new ordering, 2 is the smallest one in the ordering that exists in set 1. M of S2 is going to be, the smallest element in the set is going to be 3. All of these elements are empty. 3 is the smallest one. So it's the highest one in this set. S3. So the highest one again is 2. And M of S4. The highest element here is going to be 6. Okay, so this step's a little confusing. This choice of ordering here, this permutation was random. Once I have this random ordering, then I can say which one of those elements has the highest, of the elements in the set, is the highest ordering according to this permutation. It's the highest row in the matrix. What's the label of the highest row in the matrix that has a 1 in it? Okay? So now, what I can do is, I'm going to estimate, and so this part is going to be a little strange maybe. I'm going to estimate the Jacquard similarity between two sets as some Jacquard similarity hat of A B, which is going to be defined as 1 if M of A equals M of B, and 0 otherwise.